There is a compound that costs less than $2 at almost any grocery store, and according to several experimental studies conducted over the last century, this simple substance may influence how efficiently fuel burns inside an engine. Some early combustion experiments suggested it could help reduce carbon buildup inside engines. Others indicated it might improve burn completeness under certain conditions. A few researchers even reported noticeable improvements in fuel efficiency during controlled trials. The compound itself is not rare, it is not patented, it is not expensive. In fact, it is sitting in millions of kitchens around the world right now, and the underlying chemistry behind why it might work has been discussed in combustion research for decades. In the late 20th century, several energy research institutions began studying how alkali metal compounds interact with hydrocarbon combustion. One of the organizations frequently cited in combustion literature is the Oak Ridge National Laboratory in the United States, a major government research facility focused on energy science. Some internal studies examined how trace inorganic compounds could influence flame chemistry inside combustion systems. Later reports from European energy researchers also explored similar mechanisms while studying industrial combustion efficiency. These studies did not claim a miracle fuel additive, but they did document something interesting. Certain ionic compounds appeared to alter how hydrocarbon fuel burned under specific conditions, so the question naturally follows: if chemistry has been discussed for decades, why is it almost completely unknown outside specialized research circles? The story often referenced in early combustion anecdotes begins in 1917. During the First World War, a British Army mechanical engineer, Lieutenant Harold Fitch, was reportedly stationed in the Mesopotamian theater in what is today Iraq. He was responsible for maintaining a fleet of early motor vehicles used to transport supplies through desert terrain. These vehicles ran on fuel that was frequently contaminated with dust, water, and crude residues. Engines misfired constantly, fuel burned poorly, and replacement parts could take weeks to arrive. According to accounts published years later in an engineering journal, Fitch experimented with a number of improvised techniques to stabilize combustion in these engines. One of those experiments reportedly involved dissolving a small amount of sodium chloride, common table salt, into a water solution and introducing it indirectly into the engine's intake airflow. The results he described were modest but noticeable. Engines that had been running rough appeared to stabilize. Carbon buildup seemed to reduce after prolonged operation. Fuel usage appeared to improve slightly in some cases. Fitch documented these observations in a field report dated March 1917. The report was archived, but it was never widely studied or formally pursued after the war. For decades, it remained little more than an obscure footnote in early mechanical experimentation. To understand why some researchers considered this idea interesting, we have to look at what happens during combustion. Inside a typical gasoline or diesel engine, fuel does not burn perfectly. Instead, the combustion process involves a rapidly expanding chain reaction of chemical radicals. Many of these reactions occur in fractions of a second, and a significant portion of fuel molecules may exit the combustion chamber without fully oxidizing. This incomplete combustion produces soot, carbon deposits, and wasted fuel energy. Some combustion chemists have proposed that alkali metal ions, including sodium ions, can influence these reaction chains. In theory, they may act as catalytic participants that interact with hydrocarbon radicals. Under certain conditions, these ions may help stabilize portions of the flame front or alter reaction pathways. The potential effect: more complete combustion of fuel molecules, less soot formation, and possibly improved thermal efficiency. It is important to note that this effect, when observed, has typically appeared in controlled experimental environments, not necessarily in everyday vehicle use. However, the underlying chemistry is well known within the academic field of combustion chemistry. Similar catalytic principles are sometimes studied in large industrial combustion systems such as power generation turbines. Whether such effects translate reliably to consumer vehicles remains a subject of debate, but the mechanism itself is not fictional. Over the decades, scattered research papers have examined how trace inorganic additives interact with combustion processes. At the Massachusetts Institute of Technology Combustion Research Laboratory in the early 1980s, experiments investigated how trace metal compounds influenced hydrocarbon burn efficiency under laboratory conditions. Some trials showed reductions in unburned hydrocarbon emissions when specific catalytic agents were introduced. In 2004, researchers at the Indian Institute of Technology, Bombay, conducted fleet-level studies examining fuel combustion behavior under experimental additive conditions. Certain ionic mixtures appeared to influence emission profiles and fuel burn patterns during long-term tests. Meanwhile, chemists at the University of Leeds studied how metal ions interact with radical chain reactions in hydrocarbon flames, helping map the molecular behavior that might explain these observations. Other atmospheric studies conducted by Brazil's National Institute for Space Research analyzed particulate emissions from experimental combustion systems treated with catalytic compounds. Across these studies, results varied. Some experiments showed measurable effects, others showed minimal change. What researchers generally agreed upon was this: trace chemical compounds can influence combustion chemistry. But translating laboratory findings into consistent real-world engine performance remains extremely complex, and that complexity leads directly to the next question. If chemistry has been explored for decades, why has it never become a mainstream consumer technology? If ideas like this have appeared in combustion research for decades, a natural question follows: why has nothing like it ever appeared on the shelves of major automotive retailers? Part of the answer may simply be economics. The global petroleum and automotive fuel industry generates trillions of dollars in annual revenue. That system is built around fuel production, distribution infrastructure, engine maintenance, and a massive aftermarket of cleaning agents, additives, and repair services. For a technology to enter that ecosystem, it must usually meet several conditions. It must be patentable. It must be manufacturable at scale. And it must pass extensive safety certification before entering consumer markets. A substance like sodium chloride presents an unusual case. It is one of the most common minerals on Earth. It cannot realistically be patented in its natural form. And because no single company owns it, there is little financial incentive for a corporation to spend millions of dollars conducting the regulatory trials required to market it as a commercial fuel additive. In the United States alone, fuel additives must be registered with the Environmental Protection Agency through a process that can take years and significant financial investment. Without a company willing to sponsor that process, most experimental ideas never move beyond research papers. That does not necessarily mean they were suppressed. Often it simply means there was no clear path to commercialize them. And when an idea exists somewhere between laboratory chemistry and consumer practicality, it can remain in that gray zone for decades. Some historical experiments describing this combustion concept followed a simple preparation method. However, it is important to emphasize that modern automotive engineers generally discourage introducing foreign substances into fuel systems without manufacturer approval. In early experimental notes, researchers typically used extremely diluted saline solutions, meaning very small amounts of sodium chloride dissolved completely in distilled water. The idea was not to add solid salt directly to fuel. Instead, the compound would be introduced in trace concentrations so that any sodium ions entering the combustion chamber would exist only at catalytic levels. A typical laboratory-style mixture described in older experimental protocols involved dissolving a few grams of food-grade sodium chloride into several hundred milliliters of distilled water until the solution was completely clear. The mixture would then be allowed to sit briefly to ensure full dissolution. In some experimental engine tests, extremely small quantities of the resulting solution were introduced indirectly through intake airflow systems or controlled injection methods. Researchers conducting these trials were primarily studying how trace ionic compounds influence combustion chemistry, not promoting a consumer fuel hack. And this is where an important distinction must be made. Laboratory experiments operate under tightly controlled conditions. Modern vehicle engines contain complex electronic fuel management systems, oxygen sensors, catalytic converters, and emission controls that did not exist in early 20th century engines. Because of that complexity, many automotive engineers warn that introducing any unapproved substance, even in trace amounts, could potentially lead to corrosion, sensor interference, or long-term engine damage. For that reason, the technique described in historical experiments should be viewed as an interesting piece of combustion research history, not a universally recommended practice for modern vehicles. What you have just seen is not a miracle cure. It is not a guaranteed fuel hack. And it is certainly not a replacement for the thousands of hours of engineering that go into modern engine design. What it is, however, is a glimpse into a lesser-known corner of scientific experimentation, one that sits somewhere between early mechanical improvisation and modern combustion chemistry. This channel exists as an archive of those overlooked ideas. Not all of them are practical. Not all of them are proven. But each one reveals something about how science, economics, and industry shape which technologies reach the public, and which ones quietly remain buried in research papers and forgotten reports. Every subscriber helps keep that archive open. Every share helps preserve knowledge that might otherwise disappear into storage rooms and digital libraries that few people ever explore. If this story reached you before your next trip to the fuel pump, then you already understand why curiosity still matters. Everything referenced in this investigation, research papers, historical notes, and scientific discussions, can be found in the sources listed below. This idea did not vanish by accident. Most unusual technologies don't. They simply drift into obscurity when no one continues the work. But some discoveries don't fade quietly. Some leave behind a trail of unanswered questions. And the next vault in this archive contains one of those questions, a compound first recorded in scientific literature nearly a century ago, then quietly removed from industrial use. Why? That is the next investigation, and it opens this week.